what we were talking about, organized convection. And we saw that MCS was somewhat the generic term for anything that's persistent in time and in space, or if you prefer, long autocorrelation length and times. And then among those, the most spectacular, some of you mentioned it, is the tropical cyclone. But there are other beasts that are perhaps less spectacular and less famous, but just as interesting. And those are the mesoscale convective complexes. We saw that one of the requirements on top of being persistent in length and time was to have some sort of circular, very cold cloud shield. And then squall lines, which are elongated lines of severe rain. And we saw that a lot of precipitation comes from those mesoscale convective systems. Not surprisingly, when convection is more organized, you tend to think that the weather will be more severe. And so I promised you that we'd be talking about not only what they look like, but how they are generated. What are the processes behind those various phenomena? And so, as I mentioned, not everything is known about mesoscale convective complexes. It's an area that's booming for technical reasons, somewhat related to what Tapio was mentioning yesterday. To study mesoscale convective systems, you need to have a cloud permitting resolution, so kilometric, let's say, for deep clouds, and you need to have mesoscale domains. And that's something that we can do now, and we can do a lot of runs with this type of setting, but it was not a given before. Okay, so what are the processes that lead to convective organization? I'm not going to talk about the one that's forced by the large scale. I mentioned Hector the convector. Has someone Googled it? Yes, thank you. Someone Googled it. It looks impressive, right? This huge storm over the island, forgot, Tiwi Island, I think, yes, north of Australia. So please Google it. It's nice. But I won't talk about that because this is forced by an external parameter or inhomogeneity. What I want to talk about is how convective organization can arise from vertical shear. We already saw that the thunderstorms were different when there was background vertical shear or not. And we'll go into a little more detail about how that can give rise to squall lines. Another idea is that clouds generate waves. And I won't go into too much detail, but I want to give you the basic idea. David will talk more about waves later. So they generate waves, and those waves can propagate at different speeds depending on their depth. The deep waves tend to travel faster, and they tend to stabilize the atmosphere. The shallow waves tend to travel slower, and they destabilize the atmosphere. Now, what does that mean? If I'm a cloud, I send those waves. The stabilizing waves go further. The destabilizing waves go slower, and so it's more prone to yield convection next to me. Okay, and that's how convection can organize spatially. A cell will generate a new cell nearby. That's the idea. Yeah, I'll show that. But basically, waves that are this is the tropopause and the surface. Your cloud generates, at the early stage, a deep heating. This is convective heating. And as soon as you have a temperature anomaly, you send waves because this temperature signal tends to be smoothed through the propagation of gravity waves. So you have the deep convective heating, and as the cloud goes towards the end of its life, we saw that there was latent cooling as the rain evaporates. Then the heating looks like this. Okay, so this is Q1 and Q2. This wave warms the atmosphere and it travels faster. That's what I mean by deep. It's a mode 1, if you want. This is a mode 2. And this goes slower and it tends to destabilize the atmosphere. This idea is by Brian Mapes, by the way. Okay, and for the cyclones, you all know what's important for cyclones. Surface fluxes, right? Once a cyclone hits continents, it's usually quite unhappy. It's losing its fuel, and so we'll talk about how surface fluxes favor the intensity of cyclones. And it's called wind-induced surface heat exchange, WISHY mechanism. Yeah, so someone likes that, that's good. This is ideas by Kerry Emanuel. And then finally, I want to end with this somewhat controversial feedbacks, which was very recently discovered. This is very, very much at the state of research. In fact, as I told you, some of you work on this in this room. So I want to give you some background on what this is first, and what are the processes behind it, and why we care about this. Okay. Okay, so here's the first idea, is that if you have, and maybe I'll start with the second one, because I think it's more, merci. The first one is probably more known or more widespread. In fact, actually, I can tell you a little story. So I actually started looking at this because I wanted to have score lines in a cloud permitting model that I'm running, and you have pictures on the right. So here, this is no shear, and you recognize the popcorn convection. I'll show you animations of this very soon. And then I wanted to add shear so that I had a score line, and I wanted to know what the critical, so-called critical shear is. Critical means that the score line is exactly perpendicular to the incoming flow. And so I wanted to know what value I should put, and then I tried supercritical shear, so shear that's stronger than what you need to get an exact perpendicular score line. And there's papers arguing that if you have supercritical shear, then the score line will orient itself so that the projection of the wind is critical. Okay, so I wanted to know what the critical shear was, and I started reading the literature, and I realized there was absolutely no, there were some papers, but there was no definite answer for that, so I empirically determined those profiles. And then I went to the method module that I told you about, actually, and there's some courses on this, so I started learning about them. And they explained this theory, so the rotational theory that I'll go through in a minute. And then I was at GFDL at that time, and when you publish a paper at GFDL, you first, before sending it to reviewers, you first have an internal review. So I asked Steve Gardner to be an internal reviewer, and he actually worked with Thorpe on the other theory, so that's how I heard about it, but it was not on the method module. So I want to give you both, and I don't want to choose sides, and probably in reality it's a mixture of the two. Okay, so what does that say? Well, let's say we have a background shear, and I'm going to use the same notations as the slides. So this is the background shear. Note that usually the shear is increasing with height, something like this. But I'm assuming that I can add a constant velocities, roughly Galilean invariant, modulo surface fluxes, but that's a detail. So let's say I have a background shear like this, and then I have the cold pools spreading. Do you remember cold pools? When the rain was evaporating in the life cycle of the thunderstorm, we had those gravity waves spreading below the clouds. Is that clear for everyone? Yeah? Okay. So we have those cold pools at the end of the cloud, and this is the dissipating stage, so actually the cloud base should be maybe slightly higher. So what happens? Here I have a vorticity in the background shear. And here, similarly here, I have a vertical shear associated with the gravity current spreading, which has a vorticity associated. And now as you can see, this dipole is going to favor upward motion on this side of the cell. Okay, and that's how it is believed that dissipating cells can generate new cells, something that we've discussed, but not in that much detail. Yeah. yeah, so the background wind is you have a very strong wind at the surface, and then it goes to zero. And as I said, it's kind of weird, but usually it's more something like this, but we're moving with the, say, the mean wind, so that the anomaly is this. Okay. Okay, and so we discussed this when we saw the multi-cell thunderstorms. We had cells of different stages next to each other, and the way that a dissipating stage can generate a new cell is through the interaction of its cold pools with the background shear. Okay, so that's the first theory. And another idea is that if you have a cloud which is dissipating, the reason why it's going to die is because the upward motion that generated it is killed by the downward motion from the downdrafts. But if the shear moves this region further away from the cloud, then away from the updraft, then the updraft can, as long as it's buoyant, it can keep going and the cloud can stay there longer. Okay, so that's another mechanism by which a cloud can last longer than you would expect without any background wind shear. Okay, so it's the differential displacement of the bottom to the top that allows the updraft to remain an updraft. Is that clear? Okay, and in fact, what Steve told me is that you didn't have to have a shear like this. You can actually have a step function. You'd get the same answer. So, and there's no shear in there, no vorticity, sorry, in there. No, it doesn't. It's the same one that stays. So that's one difference. This one is a new cell every time. This one is a forever living cell. Yeah. Yeah, so that's what I was drawing here. Usually, you're right, this is more realistic. It's zero at the surface. We know friction, it should be zero at the surface. But let's say I'm moving with a mean wind. So this is the anomaly. It's just simpler because then I can draw a figure which doesn't move. And same thing for the simulations. Here I did the same thing. I had a stronger wind sorry, at the bottom. And same idea. I did actually simulations where I had the wind increasing, but then everything moves and it's harder when you want to do correlations and things like this. So for convenience, it's easier to work with a shear which is unrealistic. And sometimes you learn things about doing things when you do things which are unrealistic. Yes? Yeah. Exactly. So it's the interaction, that's exactly it. It's the interaction of the vorticity from the background wind and the vorticity from the cold pools that generates the squall lines. And I told you I'd show you animation, so let's do that. So this is a top view of popcorn convection. This is the case where there is no shear. This is from, I didn't say, this is from the model SAM, Systems for Atmospheric Modeling, which was written by Marat Karadinov in collaboration with David Rendo. I'll talk about this model quite a lot. So the top view is precipitable water, which is the atmospheric water vapor integrated vertically. So if you remember from Tapio's lecture, how much thickness would you get for precipitable water? It was how much? 25 millimeters, yes. Actually, I didn't remember, thank you. 25 millimeters. Okay, so this is this quantity. It's the amount of water vapor in the atmosphere integrated vertically. But I'm not adding the whole. This is point-wise. And I don't know if you can see the white dots. These are actually clouds. It's going a little fast. And the clouds tend to be where it's moist, as you would expect. The bottom one is the surface temperature. And here you can clearly see those cold pools that are, so it's accelerated, obviously. You can see the cold pools that are generated below the clouds. Yes, this is SST prescribed. And this is the good question. This is the surface at the first atmospheric level. Call it T surface for shortcut, but that's not accurate. It's T at, I think, 35 meters. Yeah, so it's the anelastic equations. So it's the Navier-Stokes equations. And Navier-Stokes equations, but to remove acoustic waves, you assume that the density profile has a reference profile which is only dependent on z, somewhat like the Boussinesq approximation. But instead of being a constant, it's a profile of z. No, you use it everywhere except in the gravity term. And then there are various species of condensates. So you have water vapor of water. So you have water vapor, and then the condensates you have liquid rain, solid snow. So that's what's precipitating, and you have grapple as well precipitating. And then you have cloud ice and cloud liquid. So you have 6 water species, including 5 condensates. Okay, and so what happens when you add shear? This is what happens when you add this empirically determined vertical shear. You have a very stable squall line. And if you look here, you see that actually you have the cold pools aligned here, and you tend to have new cells forming with a certain time scale. All right, and then if you go to the supercritical shear, now it's not steady anymore. It's advected downwind, but not as fast as the actual surface wind. It's not going at whatever, 20 meters per second. And similarly, this is doubly periodic. Yeah, good question. This is doubly periodic. It's very similar to the simulations that Tapio was showing yesterday, except that he was talking about shallow convection, and now here this is deep convection. So the resolution is for like 1 kilometer-ish. And I'll show 3D visualizations of this very soon. Yeah. Mm-hmm. Yeah. Yeah, it's interacting with the cold pool. Yeah. Yes. Oh, yes. So, well, actually, this thing is repeated perpendicular to the board. Yeah. Yeah, and then they end up aligning. So that's the. So it depends on the strength of your shear, actually. But the way I chose the shear, that's the way I chose the shear was to have the squall line aligning like this. Okay, this is the most efficient way because you can imagine that your gravity current now, it's not easy to draw in 3D, but let's try. Your gravity current is a line, and that's going to generate a lot of upward motion. You can imagine that if it's just one single cold pool, then the shear can also go around it, and the 2D configuration is the most efficient. Yeah, that would be my answer to this. Yeah. Sorry, yes? It is similar, except that the scales and the origin of the cold air are very different. So here I'm talking about 1 kilometer. This is actually a little shallow. This might be an artifact of the model. When I show this to people who take measurements, they say it's a little shallow, a little stronger shear. So maybe 1 kilometer, 2 kilometers. So for a front, you're talking about air masses that come from higher latitudes, and they are very deep. But yeah, it's a similar lifting mechanism. Yeah, there was another. Yes. It's not propagating. Well, it's advected at the same time, and so actually this thing will move or dissipate, and this guy will replace this one. The cloud doesn't. It's going to dissipate, but the bottom can, right? Yeah. So they can if the shear is not strong enough. If the bottom mean wind, if you want, is not strong enough. But then you have advection of this part, which is where the new cell is generated. Yeah. That's why it's empirical, and that's why it's so subtle to have a theoretical estimate, because there are some ideas. So you have the strength of the cold pools. There are some non-dimensional parameters to estimate that. Some strength of, the cold pool, some strength of the background shear. And then you have, depending on whether it's greater or smaller, you have more or less tilted clouds. The anvil will be more downwind or upwind. There's more details to this, and if you go to the method modules, you have some things about this. But yeah, that's a good point. So the reason why it looks so steady is because I chose this wind so that it would look steady, but it's more complicated in general. Yeah. No, constant, homogeneous. Exactly. It's like self-aggregation in the sense that everything else is homogeneous. The only thing is here I have an external forcing. In self-aggregation, everything is homogeneous and there's no shear. And yet, convection manages to organize. That's why it's so striking and so controversial, I guess. Yes? Again, that's because, okay, so I'm going to have to draw in 3D, but say this is the shear in the x direction, and I guess it's reversed from the animations, but so if I put it here, now the vorticity is like this, and the new cell would be formed here. Now if you could look at this in 3D, what you would get is a cold pool that looks like this, and so the new cells will align along the cold pool edge, which is now a line or an arc. That's why. So it's perpendicular to the wind, indeed. Yeah. Yeah. Sorry, I can hear you. In this case, when they put a step function, yes. It was quite theoretical, so I don't remember the details. It's so again, Steve Gardner at GFDL is the one who did this work with Thorpe. I forget the details, but I think it was more a theoretical model, simple model. So I don't remember the exact value. It might have been non-dimensionalized. Yeah. Okay, that's it for shear. So far, so good. Yeah. Yes.
So I understand how, like, once you have the squall line, it can kind of keep feeding itself.
Mm-hmm.
But how do you get from the popcorn to the squall line, like, in terms of sort of that transition?
Yeah. So I'm going to give you my opinion. I don't know if there's a. So imagine it's kind of a evolution thing. So you have a cell that's forming. It has its cold pools, and then you have a new cell forming here. But if it's isolated, it's not gonna. Again, the wind can go around. Well, if randomly you manage to have two cells that are close by, their new cells will be slightly stronger, and then they're going to be aligned again. So I think there's a positive feedback that gives you that organization. But to be honest, I haven't checked in detail, but that would be my guess. The must fit survives. Okay, that's it for shear. And again, I do recommend those modules online. There's more information on this. You have some meteorologists' points of view, which is always interesting. Okay, the other process I wanted to mention are waves. And this is something that we somewhat discussed at the beginning. But so why did brine maps look for something else than shear? People have known that shear can organize convection for a very long time. But then what he realized is that in the tropics you cannot explain all the organization with shear. Okay, most of the shear and the supercells that I talked about that are associated or that occur when there's strong shear, that happens at mid-latitudes. But in the tropics there isn't that much shear. And so you can't explain, and there's ubiquitous organization. We saw this in the OLR, in the pictures, and I hope I've convinced you that there's a lot of convective organization in the tropics. And so if it doesn't come from shear, where does it come from? And and what he studied was the role of waves. And so in his paper in '93, he argued the mechanism that I told you earlier. So the convection at the beginning will yield a deep, this is the Q1 that I drew, a deep warming, convective heating. And then at the end of the life cycle of the cloud, because you have the downdrafts, you have convective latent cooling and then latent heating. And this is Q1 plus Q2. So you have to subtract Q1 to get the mode 1 profile that I drew earlier. Maybe I should redraw them. So the Q1 and this is Q2. Okay, and as we mentioned, so the the propagating waves will propagate this signal. The warm signal, the deep signal, will go further and it stabilizes the atmosphere. The shallower the baroclinic signal goes slower and it destabilizes the atmosphere. And so that will enhance convection nearby the convecting center. Yeah. Buoyancy, gravity. Yeah. But yes, it is. Yeah. So um, you have a cloud where there's deep convection, and we saw that that tends to bring you towards moist adiabat, right? And so you have a horizontal temperature gradient, because here it's going to be warmer than outside. Now what happens in the mid-latitude is that the atmosphere is happy with the temperature gradient. You have the Coriolis force to balance it. So you get thermal wind, blah, blah, blah. In the tropics, there's nothing to balance in temperature gradient. The Coriolis parameter is very small. So the only thing that can happen is that this temperature gradient is erased. And that's done through gravity waves. Okay, so there's a buoyancy anomaly. A wave is going to be generated, and that will tend to, basically it imprints the moist adiabatic lapse rate everywhere, even outside clouds. Okay, and again, David will talk more about waves. So, yes. Oh, it's kind of a hand wave. So if you warm the interior of the atmosphere, it's more stable, right? It's not going to convect because it's lighter air above colder air. That's kind of the idea. It's kind of hand wavy. I don't want to go into too much details, but whereas if you cool the interior of the atmosphere, you can imagine that this is going to make things more unstable. Same idea as, you know, when we had radiative cooling at the top of a cloud, that would enhance convection. So you're more prone to instability. This is the part, the cooling. Yeah, this part will be unstable. Yeah. Yes. Yeah. Yes. Mhm. Mhm. Mm. Cambridge, yeah. Mhm. Mhm. Mm. Mhm. Mhm. Yeah. So there you go. So sorry. Mhm. That's what. So this wave mechanism is even relevant for mid latitudes, and so okay. So if you want to know more, John Taylor has a paper published. Okay, good. Thank you. Now, how about hurricanes? And when you talk about hurricanes, you have to show pictures, obviously. So this is Hurricane Bill. Um, and so in both cases, you see the eye forming. This is probably the most striking feature of the hurricane, this cloud-free eye. So it's very shocking when we see such a sharp phase transition between no cloud and cloud. Now you know why. What's happening in the eye? How is the air moving? Descending. And here it's going up. So that's why you have no cloud and cloud. Still quite impressive. The eye wall is slightly sloping. And some people are lucky enough to fly through such beasts. And this is the type of pictures that they have. You have the wall that's slanted and a very rich variety of clouds. Okay, but here I want to go into the process. And so this is what it looks like. As was mentioned, there's upward motion here. It's not drawn, but there's downward motion in the eye, weak downward. And how does the cyclone get energy? How is it fed? What happens is that in the moistest region of the cyclone, you have very strong winds near the surface, and that is fed by surface fluxes. Okay, so what feeds a cyclone is the fact that surface fluxes are very, very strong in the place which is very, very moist, and so you're moistening the moist region. That's a positive feedback. Okay, let me say that again, maybe the whole mechanism. So in the moist region of the cyclone, you have very strong winds and very strong surface fluxes, and that's moistening the moist region. Okay, so you all agree that that's a positive feedback. You're bringing moisture to the already moist region. And that's something that's typical of convective organization, is this positive feedback between the moisture sources, or the energy sources, and the energy distribution. Okay, so the poor get poorer and the rich get richer type of idea. Okay, and by energy I mean moistatic energy, so that accounts for moisture. So the moistatic energy increases in the high energy region, and that's a positive feedback. Okay, and you can see this is an instance where you can actually see an atmospheric phenomenon as a Carnot heat engine or a Carnot cycle. You have heating in the high energy region and cooling in the low energy region. So that's a way to extract. There's a way to extract mechanical work from this thing. Okay, so I'm going to finish by saying that these are. So this is kind of the textbook separation. It's really nice. You can separate the different processes, but in real life it's more complicated. These things interact with each other. They tend to live together and next to each other, so it makes their study quite complicated. So a cyclone can generate squall lines, and then mesoscale convective systems can turn into hurricanes, which can then give squall lines, which can become which are MCSs, but they can also become mesoscale convective complexes. So it's a more complex picture. Okay, and one thing also for tropical cyclones, there's one generation mechanism which is somewhat agreed upon. Cyclogenesis is still somewhat mysterious, I should say. We don't know why a cyclone will form from a disturbance, or not actually. Does it come from disturbances or not? Some of them come from disturbances, probably not all of them. But one disturbance that seems to be favorable to cyclogenesis are these African easterly waves that are generated within this jet. And that tends to generate mesoscale convective systems, and some of them are lucky enough or unlucky enough to become tropical cyclones. Yes? Yes? It's a different scale. It's a good question, and I don't think it's completely solved actually. There's a 2015 paper by Christopher Davis that looks at the cold pools within the cyclone. Okay, so this is a large scale. You see here, there are cold pools. This here is this size. Cyclone is very large, so it's a matter of scale. And it's unclear actually how exactly those cold pools contribute to the life of the cyclone. Yeah, so I should say, I think it's 2015. He does a CRM, or 2016, I forgot. High resolution cloud permitting simulations of cyclones, so that you have, and again, it's not easy because to resolve a cyclone in a CRM, it's expensive. I spent a lot of computing hours on that, so I can tell you it's very expensive. And if you want to run with a cloud permitting resolution, then it's only been maybe a few decades that you could do that. But that's a good question, yes. So it's a different scale. Okay, and this is a picture that I like to show. So this is again an African easterly wave. So this is a signal, this is probably OLR. No, vapor, sorry. What's an African easterly wave? It's not a... the quick answer is I'm not sure. I don't think it's a Rossby wave because the beta effect is going to be small. It's a mixed Rossby gravity. Okay, so it's a mixed Rossby gravity. Thank you. It's one of those that we had on the Matsuno plot. Okay, and so I like to show this picture of Hurricane Isabella, and I actually showed this at the summer school in Cambridge, and Michael McIntyre was in the room. He's the hardest student you can ever have in the room because he has tons of questions. And so he asked me, this is a time lapse, right? And yeah, of course, this is a time lapse. This is not a bunch of hurricanes coming down. It's a time lapse, and you do see that it comes from some disturbance. Was that? Yeah, I don't know if it depends for who. Okay, so that's for the less controversial aspects. Now, how about this self-aggregation that I told you about? So first, what is it? So as mentioned a couple times, we don't know everything about convective organization. It's somewhat of a hot topic right now. And so one way to, or a starting point for theories on convective organization are idealized simulations or idealized models. And so this is what I'm showing here. This is the popcorn convection that we saw from the top earlier without skull lines. Here the gray are isosurfaces of clouds. And the bottom is, so it's a surface temperature, but as someone noted, actually, this is constant surface, sea surface temperature. So this is the first atmospheric level. And you do see actually you do recognize the life cycle of your clouds with the cold pool spreading at the end. So it looks like it's only a kilometric resolution, but it does look reasonable. And then, so as mentioned earlier, the fact that now we can simulate on larger domains led to the discovery of something spectacular, which is the ability of convection to spontaneously organize in space. And the only difference between those two simulations is the domain size. And I think this might come somewhat as a disappointment for some people because this is a multiple equilibrium, and the climate system is complex enough. We don't need to have multiple equilibria, but there you go. Yes? No, the domain is not large enough. Yes. So it's the same model. It's still the inelastic equation. Yes, yes. Sorry, the question was, can you explain more the model? So again, the model, I should put a reference. Let me put the reference here. Okay, so that was for cold pools in cyclones. And then for the model, it's called SAM, System for Atmospheric Modeling. It's fully described in a paper by Marat Kerut-Dunaf and David Randall. I think it's 2003. And actually, the paper is interesting, but the equations of the model are in the appendix. So I think it's the appendix that was the most read of all in all the scientific literature. And so you have the full equations, but it's so it's inelastic. So it solves the momentum and water inelastic. Inelastic means we have a reference density profile rho bar, which only depends on Z. Inelastic conservation equations. And you have water under different phases. You have water vapor. And then you have the liquid rain. You have grapple. And you have snow. These are the precipitating. Okay, and then you have the cloud condensate, so you have the ice cloud and the liquid cloud. Okay, so I tried to use the same symbols as the description in the appendix. I think that's what they used. So there are 6 species. The total equation is conserved. And yesterday I told you, so the resolution that we use for those deep convective studies is about 1 kilometer. But then obviously, how do you represent, say, a snowflake at 1 kilometer? It's impossible, right? So the microphysics are very approximate. And the way it's done, basically the model looks whether air is saturated or not. Is the sponge full? Right? I should stop talking about sponge because I don't like the sponge theory, but do you reach saturation? If so, you condense. And then first it goes into condensates in clouds. So if it's saturated, you start to generate either ice or liquid. And the amount of ice versus liquid that's generated depends on temperature. If it's cold, you're going to have ice. If it's coldish, you're going to have both. And if it's warm, you're going to have liquid. It's that simple. And the function of temperature is piecewise linear. Okay, so it looks something like this. If this is the fraction of the fraction of liquid over ice. If the temperature is greater than a certain threshold, then it's all liquid. Here it's all ice. And here it's lambda liquid plus 1 minus lambda ice. So it's very crude. And there's a lot of uncertainties in microphysics. But at 1 kilometer resolution, there's not much we can do. Yeah? I don't know. That's a good question. Yeah, I think there are similar. You have other cloud permitting models like WARF and yeah. Yeah, a lot of models have actually those 6 species, but the way the microphysics is handled, I'm not sure. But then it's a little more sophisticated than I make it sound. Like you have a distribution of droplet size. It's not that yeah, but same in the other. Okay, yeah, perhaps. This was built originally from the Moeng turbulence LES. It was made deep, and Marat and David Randall added the microphysics to that. Yeah, is it the same? Yeah. Yes. We do have some ideas. Thank you for the transition. That's great. I'm gonna. There was another question though, maybe. No, there's no rotation. Thank you. Good question. There's no rotation here. What happens if I put rotation? What do you think? I get a hurricane, yes. And we'll see that you indeed get a hurricane. Yes. It's sensitive to the initial condition. Whenever you have multiple equilibria, there's a good chance there's hysteresis, and there is. So it depends on how you start, but typically it's a order 10 days, something like this. The turnover time to reach the full aggregate. Now you can see very quickly whether it's going to aggregate. But the full aggregate is about 10 days. Okay. And so at first so why is it so controversial? Well, first it's idealized simulations. I didn't say, but yeah. This is doubly periodic. I hope you saw that. If something leaves here, it comes back here. And so the Earth is not doubly periodic, the Earth is not rectangular, and it's rotating. So this is all wrong. But still, there are things that we can learn from this. But that's why it was perhaps a little controversial, especially at the beginning. And it's run in an idealized state called the radiative convective equilibrium. And we've mentioned it a little bit during the talks. There were some questions, but it was not clearly defined, so I want to do this now. And it's an idealization of the tropical atmosphere where you have no net import of energy, actually export for the tropics. Most of the tropics is sending its surplus of energy to the higher latitudes. But here we're neglecting that, and so it's saying that the radiative cooling that you have in the atmosphere has to balance the latent heating. Okay, so the atmosphere is in equilibrium between the radiative cooling and the latent heating, and surface sensible heat flux, but they tend to be small in the tropics. And as Bruno mentioned, it's non-rotating. The Coriolis parameter is set to 0. We'll add rotation at the very end to see what it does. So at first it was discovered here, but since then actually a lot more people have done work on this, and it's robust to the model, which is a good thing, and it's found in other settings as well. So maybe this thing is actually quite real. But first let me tell you about radiative convective equilibrium real quick. Yes, I'll try to explain what I think, at least. I mean, the state of the art so far. Okay, but before I tell you about self-aggregation, I have to tell you about radiative convective equilibrium. And before I tell you about radiative convective equilibrium, I have to tell you about radiative equilibrium. So let's start with that. What is radiative equilibrium? It's an equilibrium state between state of the atmosphere and the surface in the absence of non-radiative fluxes. Okay, so the only thing that you have are radiative fluxes, and radiative heating and cooling drive the atmosphere towards a state of radiative equilibrium. So the best is to actually do simple calculations to understand this. So we receive short wave from the sun, we emit long wave to space, and if you do the math, they have to balance somewhat. And that would give a temperature of minus 18 degrees. That's way too cold. Why isn't it so cold on Earth? Because of greenhouse. We have an atmosphere. And so let's add an atmosphere. And I have to say I was too lazy to make the schematic, so I stole them from Kerry Emmanuel. So similarly you receive, so now I'm going to shortcut the solar. You receive the sigma T e to the 4, where E is the emission temperature. Think of it as a solar incoming. And then you emit from the surface, but then you have some layer of atmosphere helping you, a blanket. It's emitting, it's absorbing what you sent and giving some of it back to you. And so now if we do the math, maybe I don't have to go into too much details, but you can solve those equations when you do the balance at the top of atmosphere, at the first level and at the surface, and you get a temperature which is 303 Kelvin. So it's 2 to the power of 1 over 4, the emission temperature that we had earlier. And it's a little warmer, it's a little closer to what we have. It's still a little cold. But if you want to be warmer, all you have to do is add another layer, and then you get a 3 to the power of 1 over 4. Okay, so you get where I'm going. This is how you can compute the full radiative equilibrium profile. Is that clear? I went a little fast, but you'll have the slides, and I know you can all do this math. And so when you do the full calculation, that's what Malaby and Strigler did back in '64, and this is what you get. So you have something which is very warm at the surface, decreasing very quickly. This is in pressure, so this is pretty much the part that we're interested in here, the troposphere. So what's the problem with this profile? It's very unstable. We saw that for dry convection, you needed something like minus G over Cp, or 10 degrees per kilometer. This is very unstable. This is much steeper. So that's not. It's too hot at the surface. It's too cold at the tropopause. The lapse rate of temperature is too large. But actually, so I told you we were interested in the troposphere. The stratosphere is not so bad. So the stratosphere, we can say it's in a state of radiative equilibrium. But in the troposphere, it's unstable. And so the troposphere must reach another equilibrium, which is the so-called radiative convective equilibrium. And physically what happens is that radiation tends to try to drive you towards this unstable profile. So it tends to cool the interior of the atmosphere, making the atmosphere more unstable. But then convection, we already saw that, it's very efficient. The timescale for convection can be minutes to hours, depending if it's dry or moist convection. It's very quick. And so no matter how hard radiation is trying, the convection will just be releasing whatever instability you have and mixing everything with its very efficient spoon. Okay, so in the competition between radiation and convection, the convection wins. And the observed state is much closer to the convective neutrality than to the radiative equilibrium. If convection was slower, we could expect some departure and something closer to the equilibrium of radiation only. But because convection is so fast, you never have such a departure, significant departure. So what does that mean? For dry convection, what does it mean to be close to neutral? Theta is constant. That's what we saw in this figure here that I showed of the boundary layer. So if you account for virtual effects, the virtual temperature is pretty much constant. And that's because convection is so efficient. Now, in moist convection, what does that mean? If it's really well mixed, then theta E should be constant with height. And there are measurements in the tropics, and I didn't put the reference. It might be Kerry Emanuel's book. I forgot, sorry. But it's very close to moist adiabatic in the tropics. Okay, so that's the state of radiative convective equilibrium. And again, what happens in the interior of the atmosphere here, I have a radiative scheme which computes radiative cooling of each parcel of air. This radiative cooling will depend on its temperature and its humidity content, the amount of clouds, etc. But the point is it's cooling the interior of the atmosphere. That's destabilizing. Now what convection is doing, it's taking air at the beginning of the life cycle, it's taking high energy air from the surface, bringing it towards the interior of the atmosphere, so that's stabilizing. And at the end, actually, those downdrafts, they also play a role. They take mid-tropospheric low theta E air and bring it towards the surface. Yes? Mm-hmm. Yes, so the fluxes will react to this. And here, because I have constant sea surface temperature, okay, should have erased this first. Okay, so the equilibrium here is I have the, say a net short wave, long wave radiation at the top of atmosphere, or actually let me just have a net radiative cooling. So I have a net radiative cooling of my atmosphere. So I'm only doing the energy balance of the atmosphere, not the surface, and yeah, I'm not taking the surface into account. And then, so the atmosphere is cooling, but it's also receiving latent heat and sensible heat flux. What the radiative convective equilibrium is telling you is that the radiative cooling is exactly balanced by this, okay? There is no other term, so the energy is conserved. You don't have import. If you had import of energy, you could allow for some disequilibrium, but here you don't. Yeah. Now for the surface, I don't have a closed surface, which means that, and actually if you look in this model, the surface receives more than it emits. And it's in the tropics, the problem is that if you actually take reasonable values, it is true that the tropics receive more, the surface receives more. But then what happens is it's exporting to higher latitudes. And so if you want to have an interactive surface, this is different from, sorry, from what Tapio was mentioning yesterday for shallow convection. Now this is deep convection. And if you want to have an interactive surface, then you need to parameterize the sink of energy to higher latitudes. And you can do that. There are ways. You can reduce the solar incoming. That's what most people do, I think. You can add a flux into the ocean that goes God knows where. But you have to do some arbitrary choices. Here I'm assuming that the timescale of the atmosphere is fast enough that the SST at the large mesoscale doesn't change much. It's not perfect, but it's one idealization that I'm happy to do. And just one last comment, if you run with an interactive surface, but you forget to remove this extra energy that goes to higher latitude, you run into a runaway greenhouse. Your temperature will go banana, and it's going to skyrocket. And there are some publications that study this banana. Okay, but here fixed sea surface temperature, so the atmosphere is in equilibrium, not the surface. It receives more than it emits. But that's normal because we're in the tropics, we do receive more. This being said, you're right, it doesn't account for the interaction between the surface and the atmosphere. I'm assuming that the timescale of the ocean is very slow. It's not perfect, but... okay, and so as mentioned, self-aggregation, what is it? It's the instability of this radiative convective equilibrium popcorn state. And we saw that it happens on large domains, and this is not exhaustive. This is a list of some of the papers that have been written on it. We have a recent review, if you want to have more an overview on the topic. Okay, so why do we care about this? Well, I've already told you that convection can organize for reasons that we do not fully understand, and so maybe there's hope that this newly discovered feedback can help us understand at least some of the aspects that we have been struggling with for a while. Yeah? Yes. Oh, this one? You always ask the hard questions, Freddy. What's the size? This is a... What's that? Yeah, I would say hundreds of kilometers. I would say hundreds, yeah. Yeah, 500 would be my guess. Anyone knows? You must have seen this picture before. Hundreds, yeah. That's safe, hundreds, but 500, yeah. It's big. Mesoscale. That's the right answer, mesoscale. Because that's relative, it's not an absolute number. Yeah, good point, yes. So let's say this is 15, and you can take your favorite measurement device. That's right. Yeah. So hundreds, sounds good. And you have those mesoscale systems which are ubiquitous, we don't understand them. Another reason why we care about convective, well actually, a reason why we care about convective organization in general is that this is not just clouds hanging out together. It does have a significant impact on the large scales. And what it does, it will dry, just show this, it will dry the atmosphere. This is the popcorn convection from the top that we saw, atmospheric humidity. And this is the same thing on a larger domain. It's going to aggregate. So maybe I can play both. Yes, it's only a, like what, few percent increase? Yeah. It's slightly larger. It's a phase transition. It's not smooth in this idealized setting. And so what I wanted to point out is that the dry places here are nothing like the dry places here. It dramatically dries the atmosphere around the convection. And here you have those dry holes which are very dry, so they emit from low levels. And so the outgoing long wave radiation is very strong. It's emitting from high temperatures low in the atmosphere. So the outgoing long wave radiation is dramatically increased when convection organizes. There was a question? It's okay, it's good. And another thing, yes? We have ideas. I have my own ideas. I'll mention it. On a smaller domain, it disaggregates. Yeah, it disaggregates. Yeah, yeah. There is some hysteresis, but not on the domain size. Good. It's divergent, convergent. And another thing I'd like to say is that if we could go back in time, actually, I would not call this self-aggregation. I would call it self-confinement. Because if you look here, what's obvious is that it starts with a dry hole forming. And it's actually the dry hole that's pushing the convection within those, wherever it can stay, wherever it can fit. Yes? Yeah, there are waves traveling throughout the domain. Yes, I won't mention that too much, but you're right. Yeah. Like what? Yeah, yeah. Actually, I do have waves in almost all the simulations. In fact, I showed this to Brian Mapes 2 weeks ago to see if he saw something interesting. But yeah, yeah. I do have waves, and it's normal. You expect. Yes. The dynamics. Yeah. So here, I don't want to tell too much about the process because I'll go into it. But here you have descent that tends to be reinforced. So there's a positive feedback somehow which makes the descent very efficient in the dry area. And whenever you have descent, it's becoming drier as well because you're bringing air from above, which has less humidity. And so the dry region is reinforced by itself, if you want. That's a positive feedback. And I'll tell you a little bit. We believe that this descent is mainly caused by radiative cooling. We already saw that radiative cooling is balanced by adiabatic compression, so descent. That's what's going on here. You have very strong cooling in this region that favors descent, and that favors dryness, that favors very strong cooling, etc. Yeah. Yeah. Yeah, you could. Once you understand what's going on, yes, you can. I'll show that. Yeah, yeah. I can have aggregation on pretty much any domain size now. But this is the non-twisted reality. I mean, still doubly periodic and square, but I didn't change the microphysics. Yeah. These are good questions. We'll hopefully get to it today or next time. So, yeah, so what happens when you add rotation? And Marat and Karadinov and Kerry Emanuel have studied what they call the TC world, the tropical cyclone world. And here they had fun changing the Coriolis parameter and various things. And what they wanted to get is the scaling of the size of the cyclone and the distance between cyclones. So they developed various theories for that. But the point is that if you add a rotation, you get a tropical cyclone. The model is happy to have a tropical cyclone. And since then, more people have been working on this in various geometries. This is an aquaplanet rotating radiative convective equilibrium. And what you get is, again, this tropical cyclone world. This was done by Shi and Bretherton in 2014. And if you compute the average trajectory of vortices, it starts very close to the equator. The blue line is 15 degrees north. And so they argue that self-aggregation is likely very relevant to the formation. Oh, there is. There is some circulation. It's just a snapshot, but there is. And I should say this is two different views. This is from the side, and this is from the pole. These are tropical cyclones. Oh, good. This is a vorticity. You don't see the mean wind in there. This is the relative. Thank you. This is the relative vorticity, I should have said. Yes, thank you. It's a problem when you see figures too often. You think everybody knows what they're showing, but should have described. Thank you. And yes, yeah, yeah, yeah. Otherwise, you wouldn't have. Yeah. And one other thing. So you remember this Holy Grail, this little blob that we had in the OLR anomalies. Some people have argued recently that maybe self-aggregation could help understanding the MJO, this Holy Grail. And so I'll come back to this at the end if we have time. Okay, another reason why we care is that, as I said, it's associated with very strong OLR. And so it has been argued that, I didn't say, but self-aggregation is favored at warm temperatures. And so maybe this is a way that the tropics regulate its temperature. And here is how it goes. So let's imagine that the tropics warm for some reason. Then convection will be more organized, more aggregated, more organized. And then it's emitting more to space, and it's cooling, so it's going to disorganize. So you have somewhat of a stable, or an attractor, which is a stable fixed temperature, equilibrium temperature. So that would be interesting because it means that if we warm the planet, we might move to a state where convection will be more organized to help remove the excess of energy.
How is it different from the radiative fin?
The what?
Radiative fin, rapier
Yeah, the fins, it's similar to the radiative fins. It's exactly the idea. Yeah. But Pierre Humbert was talking about the subtropics for the radiative fins, and now it's the tropics themselves that are generating their own radiator because the subtropics are not sufficient anymore. Yeah, but it's a similar idea. Yeah. I should add that the radiative impact is not clear. Yes, there's stronger outgoing long-wave radiation, but you can imagine that the cloud fraction has reduced when it's been organizing. And so you also receive more shortwave. And there was one observational effort to look at what difference does it make when convection is organized or not in observations. And what they find is that indeed you do have an increased OLR, you have an increased dryness, just like the simulations show, but you also have somewhat compensating increase in the shortwave incoming. So it's not clear that this would work, and it's unknown how that would work at warmer temperatures. I think it's still the what? Yeah. Well, the deep clouds don't, but if you change their area, and if you make the outside very dry, this is not a cloud long wave effect, this is a clear sky long wave effect. And how that will respond to temperature is still unexplored territory, or very little explored. Okay, so I see I've triggered your curiosity, so I'm quite happy. And now let's try to answer some of the questions that you have. What is the physical mechanism responsible? So we can go in the model and actually remove some of the feedbacks that are candidates for this thing. So what do we have? We have the interactive surface fluxes. The fact that surface fluxes are not the same in different areas depending on the dryness, etc. So we can remove that, or we can remove the radiative feedbacks. The fact that the radiative cooling of different regions is not the same depending if you're, whether you're moist or dry, or if you have clouds, etc. And we can do this for the long wave and the short wave. And so this is a top view of sensitivity simulations where we homogenize the surface fluxes, the short wave, and the long wave. And when I say homogenize the long wave, I mean at each height. It can still vary with height. It would be a little brutal to homogenize over the whole 3D domain. But you can homogenize horizontally. And we see that the long wave cooling is actually crucial. So it's long wave cooling. It's consistent with what we said earlier, that it's the cooling that generates this subsidence and that enhances this dryness in the dry, whatever, blob or pocket. Some people call it the radiative cold pool. So it looks like a cold pool where convection is suppressed, but it's not generated by evaporation of rain, unlike the ones below clouds. This one is generated by cooling, radiative cooling. Okay, so maybe I'll skip this. And so you can ask, is it the long wave from the clear sky, from the liquid clouds, or from the ice clouds? So you can do the same exercise, and you only homogenize the water vapor that enters the radiation scheme. You remove the cloud liquid, or you homogenize as you want, it doesn't change anything. Or you remove the ice, and the winner is the liquid cloud amount. So it's the liquid clouds that matter. And obviously the question is, why? And so this is probably the hardest slide. This is the mechanism that at least a few of us believe is key for the aggregation. So let me spend some time on this slide. Okay, so what I'm showing here is the same as this aggregation simulation in 3D that we saw, but I've changed coordinates. Now I've put all the dry columns here and all the moist columns here. Because I don't care if it's at x equals 2 or 4, what I care about is whether it's a dry or a moist column. So we stratify the data by humidity, or moist static energy, it's the same thing. And this is height. Yes, in this case averaged. You can do both, but in this case averaged. So these are the dry columns, dry in the sense of vertically integrated, and these are moist columns. And as we mentioned, so moist static energy, if you remember, it has a temperature contribution and water vapor, CPT plus GZ plus LQ. The fact that you're dry or moist will determine whether you have a low or a high moist static energy. And the reason is the temperature contribution is very small because, as we said, there's nothing to sustain a temperature gradient in the tropics. There's no rotation. So there's no geostrophy. So if you have a temperature gradient, it's going to be homogenized very efficiently by waves. Okay, so the temperature variability is pretty much negligible. So the moist static energy variability is dominated by the water vapor variability. Is that clear, or is that, want me to write it? No? Okay, so so this is, you can think of this as water vapor content. Okay, so the top shows the moist static energy in color. And the reason why I plot moist static energy, because I want to see how the energy is transported. And I want to find this positive feedback. I want to see whether The circulation is exporting energy from the low energy, pore get poorer, and putting this energy into the moist region. The rich get richer. That's a positive feedback. Okay, so that's the goal, and that's what I'm going to show here. The circulation is shown as black lines. This is the stream function in this weird space. And you have the cloud in white and in pink. I didn't choose pink, but the reviewer wanted another color, so you have to choose your battles, and I thought, okay, let's put it pink. And here what you see that the circulation is somewhat what you would expect. So you have upward motion in the moist region, where you have deep convection, and that's where you have the clouds. And then there's outflow in those anvil clouds and upper level circulation. Here you start having radiative cooling, no more latent heat, so it starts to descend. But then here, instead of returning as it would in a regular popcorn simulation, it keeps going very low, and then it returns very close to the bottom. And this is really what is specific of self-aggregation, this low-level circulation. So how is that associated with this rich get richer and poor get poorer? Well, if you look at the moist static energy in the background, if it had returned here, the moist static energy would have been pretty low. But because it's very close to the bottom, the moist static energy is much higher. And so it is transporting high levels of energy towards the high energy region. Okay, so it's really this low level circulation which is key. You need, sorry, what? Not necessarily. In a typical popcorn convection, you'd have this flow here. Like the total circulation is constrained by some energy balance, but this is at the very beginning, during the onset of aggregation. So actually, we do have some departure, but the overall circulation will have a constraint, but not the low level is the one which is key, and it's the one that changes. Don't know if I answered your question. Okay, so but what's the connection with the radiative cooling? Yes, sorry. No, it depends on whether this circulation develops. This low-level circulation between dry and moist region develops. And so it depends pretty much how low the circulation goes. And it depends on initial conditions for reasons that will become clear, but basically it's related to what generates this descent here. The key is that you have descent here, and that's pushing the return flow very low. So it's related to the low clouds, as we saw, the liquid cloud, and it depends on the distribution of liquid clouds, basically. Yeah. And in fact, even the domain size, you can show that the domain size has an impact on the low-level cloud amount, and that's why it's sensitive to the domain size. And how does that relate to the low-level cloud? That's the last piece of the puzzle we're missing, so let's discuss this. This is the same figure, but I'm showing the radiative cooling rates now in color. And unsurprisingly, where we have this very strong descent, we see that there's very strong cooling contribution from either clear sky or low-level clouds. Remember, clouds are associated with the cooling above them, because there's a lot of emitters. And so here's the picture that we have in mind. There's very strong low-level cooling in the dry region from clear sky and low-level clouds. That generates subsidence, because you have to balance this cooling by subsidence warming. And that forces the return flow to be very low, yielding this rich get richer and poor get poorer positive feedback. No, that's long wave. Yeah, that's long wave. Yes, that's long wave. It is, but this is the vertical distribution. This is not the top of atmosphere. Yes, yeah, good point. This is the vertical distribution. Yeah.
The fact that it's low is crucial because
Yes.
it's low enough.
Yeah.
It picks up moisture from the
Yeah.
surface.
Yeah.
It's not low enough.
Exactly. Yes. So that's key. Exactly. Wow. Yeah. Okay. So if you understood this, this was the hardest slide. So congratulations. And so actually at this point, I have another story to tell. So at this point, we were quite happy. We started writing the paper, and then one of the reviewers said, "Oh, that's all really nice," or maybe he didn't say that, but he said, but okay, so if the low clouds are so important, where are them? Where are they?" And yeah, I have to admit he had a pretty good point. So we went back to work a little more, and we thought maybe maybe you need the the low clouds to start the aggregation, but maybe once the aggregation is formed, like here, there's another feedback excited. Maybe that's why there's hysteresis and sensitivity to initial conditions, because if you have different feedbacks, you can excite them with different initial conditions. And so we did another experiment to investigate whether that was the case. And so the top one is after 10 days of simulations where we remove the long wave effect from low clouds. And this is the same simulation, except that we only remove the low clouds after 10 days. So here, up to 10 days, they are similar. They're not similar. This one has low clouds, this one doesn't. If you don't have low clouds, we just saw that there's no aggregation. If you have low clouds, the aggregation starts. But now here, I'm going to remove the low cloud long wave effect. And you can guess what's going to happen. Aggregation remains. So there's something that you have to know about aggregation, is that it's when you think you understand something, you should always think twice. In fact, some people call it self-aggravation, because it's really annoying, but it's anyway. And so what does that mean? It means that the mechanism which is responsible for the onset, the low-level cloud long wave effect, is different from the mechanism that is responsible for its maintenance. Or you can have two mechanisms responsible for the maintenance. And it turns out to be the clear scale and high clouds. If you remove all the long wave, just to be sure we removed all the long wave, then yes, you do lose the aggregation. Okay, so very quickly, I just want to go through some other thought experiments that we did to try to understand exactly what aspects of the long wave cooling mattered. And in fact, since then there have been more people working on this, and there was a lot of variety of processes in the literature, so we wanted to clarify all this. And so the cloud radiative processes, that was what we argued was or what we found was important. And then there's a theoretical model that showed that clear scalar radiation could also yield aggregation without cloud radiative effects, especially at warm temperatures. And all the work that I had done was at a fixed 300 Kelvin temperature. So it was still unclear which one mattered. Depending on the temperature, the leading order mechanism might change with temperature. And I think it's still an open question, actually. And then there was a theoretical paper that argued that moisture feedback, so if you have convection, you tend to moisten this environment. That's a positive feedback. It's going to favor convection at the same location later. And maybe just this moisture feedback is sufficient to yield aggregation. And then Givenchy and Roms have showed that cold pools might be responsible for the domain size sensitivity. And so obviously, like, what do cold pools have to do with anything? So we wanted to clarify all this, like which aspects of physical processes matter for aggregation. So we're going to do idealized experiments. And here's the experiment. So we know that the radiative aspect, or we believe the radiative aspect matters, the long wave radiation. And what matters is that the long wave radiation profiles are different in the moist and in the dry regions, right? The colors that we saw. And so what we did, we computed the we took an arbitrary simulation that aggregates and look at the radiative cooling profile in the dry region and in the moist blob. So in the dry region, you have a fairly constant -2 Kelvin per day cooling until you reach the surface where you have this enhanced cooling that we saw in the weird variable circulation. So in the dry region, you have this bottom enhanced cooling that's consistent with what we saw. In the moist region, well, you have the signature of clouds, basically. So you have cooling above clouds and warming below clouds. So you have lots of wiggles. And so we thought, okay, so it's somewhat the difference between those two that seems to matter for aggregation. Which aspect, which feature And so we did a few idealized experiments. So we put some wiggles and then the constant cooling in the dry region. Then a homogeneous, somewhat constant cooling, and then one where we enhanced the cooling in the dry region. And then we go in the model and we say, so the radiative cooling is no more a function of your conditions. We just impose the blue profile if you're dry, and we impose the red profile if you're moist. Okay, so let's take, who thinks the first one will aggregate? The second one? Third one? Good, okay. Yeah, so if you believe what I said, if you homogenize the long wave horizontally, and now whether you're dry or moist, that doesn't change. It's the same profile everywhere. Nothing will happen, hopefully. We'll see. You never say never with aggregation. So we saw that we believe the dry region is really key. And so the wiggles of the moist region should not matter too much. But this low level cooling should be what matters. Okay, let's check. And you win. It is this one. Note that if you impose this low level cooling everywhere, you do not get aggregation. Okay, so it's indeed the difference between the dry and the moist region. And as someone mentioned, if you put it slightly higher, it still doesn't aggregate. So the fact that it's very low is key. Okay, so I'll skip the circulation. We've seen this. And the question is that the whole story? No, there's still some other puzzlement. So we saw we don't need the low-level clouds to maintain aggregation. So let's do the same exercise, only accounted for the high cloud amount. So now this is another control simulation where I do not have low clouds in the radiation. The clear sky actually changes. You don't have the cooling that we had was partly due to low-level clouds. Okay, but we do have a little kink here, which turns out to be important. And then you only have the high cloud signature, so cooling and warming below the high clouds, ice clouds. And so I won't quiz you again, but you find that what matters is actually this small but important low-level cooling and this mid-level warming. Okay, so that's confusing, but actually maybe it's the same mechanism, and we believe it is. The difference is that you still have this low-level cooling, which generates descent, but it's weak, so it's not sufficient. You need the help of someone pulling the air on the other side. But the picture is, in fine, roughly the same. Okay, so now how about cold pools? What role do they play? And so then we started a simulation where we said, okay, let's remove cold pools and see if indeed it does help aggregation. So how do you remove cold pools? How would you remove cold pools if you had to do a simulation like this? Yes, exactly. We know cold pools are, so the drag of the hydrometeors does matter, but the evaporation of rain, which cools the air through latent cooling, is generating most of the force of the gravity current. So I started a simulation where I remove the evaporation of rain in the first kilometer, but the long wave cooling is homogeneous. And if you remember, aggregation is not allowed when the long wave cooling is homogeneous, and yet here it is in your face. It is aggregation, but it's a different one, somewhat. So what we argue is that this is very new. This was published in 2015, and we don't understand this mechanism very well. But our argument is that for some reason convection starts somewhere, and because you don't have downdrafts for the cloud to kill himself, the updraft just stays there forever. Okay, that's the argument. But I think more work needs to be done on this. Okay, and so I'll just end on two very recent exciting results. One that I heard about 2 weeks ago from Marat Keredinov and Kerry Emanuel, the Holy Grail. So if you remember, this is the OLR anomaly, and we have this blob here, which I told you a lot of people have been working on, and I was going to say failed miserably. That's a little harsh. No, we understand quite a lot about the MJO. There has been a lot of interesting work, but still there's, I think, a feeling in the community that we haven't completely solved this problem. And so what Marat and Kerry did is large domain simulation, tropical channel simulation with this cloud resolving model, and then they looked at the variability that they had, and they found an MJO. and they can relate this to self-aggregation feedbacks, the long wave feedbacks. So maybe actually we have a new angle to study this process. Maybe self-aggregation feedbacks actually matter for this thing. Another exciting result, it's mine, so obviously I find it exciting. So with David, we've been working on what happens when you add rotation. And as mentioned, in a control run, the rotation gives you a cyclone in about 20 days. This is the variability of moist static energy, and as mentioned, variability is associated with organization. Now, if you remove the self-aggregation feedbacks, it takes 3 times longer, 2 to 3 times longer. And this is robust to initial conditions. These are the ones with the control runs, and these are the ones where I remove the self-aggregation feedbacks. So maybe actually this, I'm not saying we solve the cyclogenesis problem, but maybe this is going to help shed new light into this important problem that we don't fully understand. Okay, and so just finish on my summary, and since I'm exactly at 30, I'll stop here, let you read. Thank you. Yeah.
Just a small question on the radiative transfer calculations, obviously critical to everything.
Yes, yeah.
This is still done column-wise?
Yes, so the radiative cooling, the radiative scheme does things column-wise, yes. Yeah, so there are some, there are people thinking about the fact that when you have radiation coming into a cloud, it's not vertical, you have 3D structures and they have some, I don't know the details, some random path. Yeah. Yeah, yeah. But here it's not super reasonable. No, I agree. It is an approximation. There are a lot of approximations. I would say the radiation and the microphysics are probably. And that's why I think whenever you run a model like this, you can decently compare simulations. So for instance, the ones where we impose the differential radiative cooling rates, this makes sense. And we can actually measure radiative cooling rates from observation, in situ measurements. But I do agree that every result should be taken with a grain of salt. And this is a large uncertainty. And that's why we wanted to understand exactly what feature of the radiative cooling profiles mattered. Yes. And I did see though some recent exciting talks about the 3D structure of clouds and how that interacts with the radiation. And people are starting to think that maybe we should take that into account. Yes, but that's a good point. The microphysics and the radiation schemes are probably the largest sources of uncertainty. Maybe the subgrid scale as well, turbulence, parametrization. Thank you. Thank you. Yeah, that is a good question. Yeah. Yeah. Yes. So this has been looked. So originally I only got one patch, and I tried really hard. And I was telling some people yesterday that I visited MPI for a week, and then Bjorn Stevens asked me this, and then he kept coming back to my office like, do you always? I said, okay, I'll try. And so I made a bigger domain, and I tried really hard. I made 4,000 kilometers. I still had one patch, and I seeded 2 patches, and they merged. But then since then, more people have done work, and I think David Randall actually has worked on this, and they did an the problem is these are expensive runs. Right? You have to run really large domains, but they do have a scale that emerges around 7,000 kilometers. Da is going to talk about this afternoon. I don't know where he is. Yeah, here this afternoon, right? You give a talk about the scale. Yeah, and also Alison Wing, Tim Cronin have done. They realized that it was very expensive to do square domains, so they did rectangular domains. And in that case, you do have a scale that emerges. So we believe that there's a scale. The reason why I only get one blob is because I have limited my domain size. Yeah. Yeah. Yeah, so you're right. Yeah, that was 3D, I should mention. And I think it's 7,000 kilometers. Do you remember? Something like this.